Hi, this is Dr. John Bergdorf. In this video, we're going to explore some of the basic operations on sets, and we're going to do so using manipulatives. Manipulatives are objects that one can handle with one's hands and move around to explore mathematical concepts in a kinesthetic manner. My manipulatives in this example is a collection of buttons. Some of them are square, some of them are round, some are yellow, some are black, some are kind of a grayed out yellow, some have 2 holes, some have 4 holes. This is going to be what I'm going to call, for my purposes for this video, my universal set. A universal set is the collection of all objects that could be used as elements of sets in a given situation. Now, that does not mean the universal set is truly universal, as in the set of everything, which would be interesting, but simply the set of objects that are being used in a given context. If I'm going to be kind of manipulating these buttons, then my universal set is simply this collection of buttons. And we usually denote universal set with the symbol U. Based on that, we're going to define our second really definition, first definition particularly about set operations. The complement of a set A, which is denoted by A with a bar over it, is the set of all elements in the universal set U that are not elements of A. Let me illustrate that with a Venn diagram. This picture is a Venn diagram. The large square represents the universal set, and within that set, I have a set A. Now, I'm going to play with this with specific definitions. Let A be the set of round buttons. So I'm going to go over here to my collection of buttons, and I'm going to represent them by putting them all inside the circle that represents A. Here go all my round buttons. And I'm going to have to overlap them a little bit, get them to fit. Round buttons, round buttons. There they go. Now the deal is, these buttons over here, these square ones, they're part of the universal set too. So they've got to be included in this large square, but they can't be in A. So where do we put them? Well, we'll put them outside of A, inside the universal set, but outside of A. This is going to exactly connect us to the concept of a complement. If A is the set of round buttons, then A complement is the set of square buttons. And in the context of exploring Venn diagrams, what that means is that if A is represented by the circle A, that's denoted A, then A complement would be the region still within the universal set, but outside of A. So we often connect back to Venn diagrams by sketching what that would look like. If A represents this circle and U is my universal set, then A complement would be all the region outside of A, and I might shade that like that. And that's a visual representation of the kinesthetic exploration that we did on complements. All this area out here that I'm shading in red would be A complement. So we have our kinesthetic model, we have a visual model, all dealing with the idea of universal set and complement. Let's explore some more definitions. In this definition, we're going to look at having a universal set that contains 2 sets. And to demonstrate that any 2 sets could have something in common, we show them overlapping. What we're going to define in this picture is the concept of intersection. So if I have 2 sets within my universal set, the intersection of the 2 sets, A and B, is the set of all the elements that are both in A and in B. And the symbol for that looks like sort of a U turned upside down. All the elements that are in A and in B. Let's use a different Venn diagram to represent that. Here's a larger one, just it'll be easier to work with. But let's go with this definition we have here. New definition. Let A be the set of round buttons. So actually that's what we had before. Let me get all my round buttons back. Put them here in A. I'm just going to dump them in. Not really thinking about it very hard right now. But here come all the round buttons. Here's some more round buttons. Just dumping them all in A. And then, I think that's all the round ones, yeah. And then B, it says, is going to represent the buttons with 2 holes. Well, that's interesting. Let's get, I see a problem here. Some of these round buttons have 2 holes. So they should be in A, but they also should be in B. Well, where do we put them? That means they're going to have to go right here in the middle. This would be both part of A, which is the set of round buttons, and part of B, which is the set of buttons with 2 holes. So these round buttons with 2 holes will have to go in here. These are also round buttons, so I leave them out. Oh, there's another one with 2 holes, so we put that in there. What about what's left? Well, some of these have 2 holes. So we said that we wanted all the buttons with 2 holes to live over here in B. These would be the round ones, but there'd be some square ones, and there's still some buttons left. And they will lie out here outside of both A and B in the universal set. So where is my intersection? Where is my intersection? Let me slide that back down so we can see it just a little bit better. The intersection of the 2 sets A and B is the set of all elements that are both in A and in B. They have to be both in A and in B. That would be these buttons right here in the middle, that crossing area. If you'd like to think of the word intersection in a more informal way, think about the intersection of 2 highways. You've got 2 streets or roads or something intersecting each other. That intersection is that place that is both on one road and on the other road. It's that crossing point where the light is. So this would be my intersection, the set of round buttons with 2 holes. I can illustrate that going to a visual model from a kinesthetic model. The region where the round buttons with 2 holes lay was this region in here. That's a pictorial representation of A intersection B. Now, let's look at another concept. These out of the way, get a new one. Let's talk about the concept of union. The union of 2 sets, A and B, is the set of all elements that are either in A or in B, or both. Now, intersection was the set of elements that are both in A and in B. Union, the elements are in either A or in B. So the key words union or and intersection and. My definition here is going to call for us to use the same set of buttons that I had before. Let A be the set of round buttons and B be the square set of buttons with 2 holes. Let's see if we can figure out where A union B is. Got to get everyone back on the picture well here. Tell you what, let's move these up here so we don't miss them. Going off the bottom of the camera a little bit. And straighten that up. Where is A union B? So intersection had that idea of the buttons that are both in A and B. Union has the idea of all the buttons that are either in A or in B. All of these round buttons are in A, so they're in A or B. All of these buttons with 2 holes are in B, so they're in A or B. And it says A or B or both, and so that includes the elements in the intersection as well. The union would be all of these buttons, except for these guys in the outer area beyond the two sets. So if you want to have a way to think about union, think about a labor union, say, where you have all the workers in a company all working together. They're all part of this union. We're all in it together. So union means take everybody. Take all the elements that are in A, take all the elements that are in B, take all the elements in both. All of these round buttons that have 4 holes, the round buttons with 2 holes, these square buttons with 2 holes, just not these guys that refuse to join out here in the outside. Let's again go from the kinesthetic to the visual. The union would be all the elements that are either in A or in B or in both. The union would be all of this. The symbol for union looks like a U, and that probably makes a lot more sense than the intersection symbol. A U shape for union, and I guess an I would not have looked so good. So for intersection, they just took the union symbol and they turned it upside down. So that's union, and that's intersection, and we've already talked about complements. We're going to go back to, we're going to observe something interesting that happens when you compare the cardinalities of unions and intersections. Excuse me a second, my paper wants to stick together. So for this example, I'm going to need to get my kinesthetic model back out here again. But I want to count how many elements there are in A, in B, and then in the union and intersection. Same definition of A and B, so I'm going to use the same pictures that I had before, like that. Let me straighten that up just a little bit, and we're going to count. So this is the symbol for cardinality. We've seen that before. It means the number of elements in A. Let's slide A up a little bit so we can see it a little better, and we'll slide back down. How many elements are A? Count the buttons that belong to set A. That would include not just the buttons that are here, but also the buttons in the intersection, because they are part of A too. And I am counting 1, 2, 3, 4, 5, 6, 7, 8. 8 buttons in the circle I've labeled A. So the cardinality of set A is 8. How about set B? Slide that back up again. Set B would be in the middle where the intersection is, but also these 3. So 1, 2, 3, 4, 5, 6, 7. I'm counting 7. But let's also count the number of elements in the intersection and in the union. Intersection, again, is all the elements that are both in A and in B, where the 2 streaks cross each other, where they intersect. 1, 2, 3, 4. I see 4 elements in the intersection. Whereas the union, like a labor union, means we're all in this together, whether you're in A or whether you're in B, take everybody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I'm seeing 11 of those. Now, the interesting thing is there is a relationship between these numbers that will make a lot of sense when you think about it. Let me show you what it is. Notice that the number 11, you can get that by taking 8 plus 7, which is 15, minus 4. This number is this one plus this one minus this one. Or symbolically, more generally, what we have is that the number of elements in the union is equal to the number of elements in one set plus the number of elements in the other set minus the number of elements in the intersection. That's an important formula we'll see several more times in the future. And I think we can make sense of it. If I'm counting all the elements in the union, which would be all of these guys and all of these guys, if I did it by saying, okay, I'm going to figure out how many elements are in A and add them to how many elements are in B, Notice that I'd be counting the buttons in the intersection twice. So if I just said n of A plus n of B, I'd count these fellows twice, and I'd have to fix it by subtracting off the number of elements in the intersection, so I'm only counting it one time. So very important theorem, and I hope that makes sense. Let's just play with some more examples of unions and intersections and complements and begin to get them all together here. We're going to use the same set of manipulatives, the same buttons as before, just like always, but this time we want to find A intersection with the complement of B. Let's see if we can figure out that. So B complement, we've seen that already. That's all the elements that are in the universal set but are not in B. Let me move that up just a little bit. B would be these buttons here, these four in the middle and these three over here. B complement would be everything outside of B. All the elements in the universal set except the ones in B. That would include these four square buttons with four holes out here in the outer area, but it would also include these four buttons, four round buttons with four holes in A, just not as part of B. So what sometimes people find easiest when they're doing this visually is to say, well, I see there's two things I'm going to be doing here. I'm going to be looking at both the complement and an intersection. Let me just do one part of that. Let me suppose that I represent B complement with green hash marks. So B complement would be like everything outside of B. I'm going to represent that visually, going back and forth from visual to kinesthetic and back again. Just that would be B complement, which is not the only thing they're asking for, but it helps me visualize the area. What I'm looking for is the intersection of A and B complement, which we'll come back to the visual in a minute, but let's look at the kinesthetic first. If intersection means, like we said before, the crossing point place of the two streets, and B complement represents these round buttons and these square buttons that are out here, the intersection, the set of buttons that are both in the complement of B and in A, would simply be these round buttons with four holes, just that area right in there. So I might do something like this in my visual sense. I might say, okay, what does A look like? A looks like this. Just A itself. And the intersection of the two would be those elements that are both in A and the complement of B. It's basically the region that's colored both ways, both red and green. And then I might go in and color that in a more pronounced way to really illustrate that that's the region I'm concerned with. A intersection B complement. Let's do another one. And again, we're going to jump back and forth. We're going to look at it kinesthetically and then also visually. Each stage, I'm making it just a little bit more complicated. Not too bad, I hope. Same sets of buttons. A is the set of round buttons. B is the set of buttons with two holes. So I've got them all in the same place. I want to this time explore A union B complement. Now, in sets, much like in the rest of mathematics, if you see parentheses, it means do this first. So this is saying first look at A union B. And then take the complement of that. I'm actually going to pause in speaking here to let you have a chance to see if you can think of where those are, which buttons belong to that. If you first of all start with the union and think about where that is, and then take the complement of that union. And I'm going to shut up for a second and let you think. All right, I'm back. Let's see if we can figure that out. Union, again, the idea of a labor union, we're all in this together. Whether you're in A or whether you're in B, we're all working together. So the union would be all of these round buttons, the round buttons with 4 holes, the round buttons with 2 holes, plus, and that one's trying to get in, the square buttons with 2 holes over here. All of these guys in here. And the complement of that would be the set of all the elements that are in my universal set, but not in that union. And that would be the square buttons with 4 holes in this outer region that's outside of both A and B. Did you get that? Hope so. Let's look at where that would be. So again, what you might want to do is use a couple colors, because we're doing 2 things. We're first doing a union and then taking a complement. A union B, we know. Let's suppose we do that in red. All the elements that are either in A or in B or in both, all of this area here. And the complement of that would be all the region outside of what I've got colored in red so far. In fact, I think I'll draw it in darker so it's clear that that's my sort of final product. It's all of this outer region out here that is outside of the union of A and B. All of that outer darkness in the universal set, but not in the union. So it'd be that green area. Hope that makes sense. All right, guess what? We have one more definition that we want to explore. And we'll do this again using our manipulatives. We're going to have the same buttons, which have gotten a little bit messed up. So this gives me a chance to make sure that I get them right again. Let's go to the example first and get them straight. A is the set of round buttons. So all the round buttons belong in A. But B is the set of buttons with 2 holes. So the round buttons with 2 holes have to go in the intersection. The other buttons with 2 holes have to go out here. And here's, that one got out of place. So there we go. We're back. We are going to talk about a concept called relative complement. And this is going to sound, when you first look at the definition, like it's way too complicated. It's actually, I can make it sound much simpler. The complement of A relative to B, written as B minus A, is the set of all elements of B that are not in A. An easier way perhaps to say that is to say, start with B, take away elements of A. And that idea of subtraction will be really, really clear here. So I have all my elements of B, all of these buttons in here. The relative complement, B minus A, would say start with B and consider all the elements that are in B but not in A. Start with B and imagine taking away the elements of A. So these elements are in B to be sure, but they're also in A. I would want to take those away, leaving only these square buttons that have 2 holes as all that's left. That would be my complement. In visual form, it's basically this sort of like waning moon shape, let's say. or maybe a moon that's under a partial eclipse, that's part of it's blocked. That would be B minus A, starting with the set B, removing any elements that are part of A. Just to make sure that is cool, let us, oh dear, I bled through there, sorry about that. Let's explore what we would mean by A minus B. So if we have the same buttons, but I want to explore A minus B, that would mean start with A and take away anything that is in B. Tell you what, bear with me a second here. I've got one more page and I don't want the ink to bleed through again. Start with A and take away the elements that are in B. So in my picture here, A is, now we're doing it the opposite. We're starting with A, but we're taking away any elements that belong to B. So we're starting with all the round buttons, but we're taking away the round buttons that have 2 holes, and it would just be the region where you have round buttons with 4 holes. So A minus B would be this eclipsed moon shape over here. And with all of these things, we've explored a number of very important concepts, which I'll make a list of. And we've done it by looking at a kinesthetic model we can put our hands on and play with. We've also looked at it visually. And the concepts that we have explored are universal set, complement, intersection, union, and relative complement. What I hope for now is that by exploring all of these things kinesthetically with manipulatives and then visually with diagrams, is we can move to a more abstract setting, moving all of our pictures out of the way and all of our buttons out of the way, where we just explore these same concepts with specific numerical examples. So we're putting all the buttons away. Well, you'd still see them there, but I'm going to define a new universal set, and I'm going to try to explore some of these ideas. So without manipulatives, I have a new universal set. The set of interest to me, again, it's not necessarily the set of everything, but in this case, it's the set of whole numbers between 1 and 10. A will be the set 1, 2, 3, 4, 5. B will be the set 4, 5, 6, 7, 8, and 9. Let's explore some of these ideas. Complement. All the elements that are in the universal set, but not in A. So A consists of 1, 2, 3, 4, and 5, the set containing 1, 2, 3, 4, 5. The complement of A would be the elements of the universal set that are not part of A, 6, 7, 8, 9, and 10. Intersection, like the intersection of 2 streets, would be all the elements that are both in A and in B. So I'm going to look at A and look in B and see if they have any elements that are in both of them. And I believe I see that both 4 and 5 are in both A and in B. So that's the intersection. Union, the set of all elements that are either in A or in B, include everybody, include like a union, like a labor union, take everyone from A, take everyone from B, put them everybody all together, one big happy family. Anything that shows up in either A or B would include 1, 2, 3. They're all in A. 4 and 5 are in both sets. 6, 7, 8, and 9 are in B. So we include them as well. As you get more complicated, it might be useful to take this in pairs. Instead of trying to look at the entire operation A intersection B complement, you might want to start with thinking just what's in B complement and then look at the intersection. So B complement would be everything that's in the universal set but not in B. B are the natural numbers from 4 to 9. So what's not in that set would be 1, 2, and 3, and then 10. That's B complement. But the intersection of A and B complement would be all the numbers, all the elements that are both in A and in B complement. Are there any that overlap in here? It looks like 1, 2, and 3 would do it. Those numbers are both in A and in B complement. A union B, and then the complement of that. Again, you might want to do this in 2 stages. Parentheses means do this first. So you first think about A union B, all the elements that are either in A or in B, and we've actually done that. It's everything, in fact, except for the number 10. And the complement of that would be all the elements that are in my universal set, but not in this set. That's my intersection. So union. So what's not in that set? What's left? What's not in here that is in the universal set? Well, nothing but the number 10. So we create that set. B minus A, the relative complement. Think of that as starting with B, but taking away from B any elements that are also in A. So if I look at B, notice that B includes the 4 and the 5 that belong to A. I'd have to take those out, but keep everything else. 6, 7, 8, and 9. And finally, A minus B, I'd start with A, but take away anything that belongs to B. So looking at A, it includes a couple numbers that are in B, namely the 4 and 5. I'd have to throw them out, and I would just have the set containing 1, 2, and 3. So I hope in this video, by starting with something kinesthetic, we've been able to explore some really important set operations. And now that you've got that idea, I hope really, really well, you can do abstract questions and apply those to other situations. Thank you so much for joining me.